Here we are. Bunch of stuff to go over. So this is all on circular motion. Circular motion. And let's zoom in a bit. All right. So I'll hit autofocus. Okay. So the idea is that we're going to cover this, and then you're going to have uh, an assessment assignment. Unless, in the next pack of material, you should get a set of questions, and I just want you to try to do them yourself to basically see if you're learning the material, if this is working, basically. Um, so, it's kind of like a test, but, you have your book, you have whatever other info you need. But what we've got is another set of material, and this is motion that's in a circle. All right? The idea here is you can go through and prove certain statements, about the geometry of something moving. Right? We have something that's going in a circle, and we can talk about the velocity, which at two particular instances might look like that. And based on the velocity and the radius that we have, we can essentially build that there has to be some acceleration toward the center of the circle. And what we get out of it is that the acceleration looks like v squared over r, where this is r on the interior. Right, so that's in your textbook. That's in the notes, I believe. It's not a crucial thing to know, but it's one of those things where basically the way to solve this easiest is through geometry. Is to say, hey, there's similar triangles here. You have one that's this one with v initial and v final and delta v. And then you have the one that's interior to this circle with the radiuses and the change in position. And this is just saying that delta v over v is proportional to delta r over r, which if you solve this out by putting in a delta t and letting it go to 0, then you get this acceleration. Now, this stuff's a circular motion, and you can still do velocity as distance over time, right? The distance now is 2 pi times the radius. So we also have that the velocity is 2 pi times the radius over the time. You have this time here is what we call the period. Because this is a periodic motion. This is one of the first examples we have of something where we don't have to describe all of the motion. We just have to describe the bit that repeats over and over. So if this is something moving in a circle, well, once it gets back to this point, once around clockwise, it'll just do it again. So, periodic motion is very nice because we don't have to describe the whole thing. We can just describe a period of it. And so the time that it takes to do that's important. Now, you can relate these things if you would like. You can plug in for the velocity, and you would get something like the acceleration is 4 pi squared r over t. I believe that's right. 4 pi squared r squared divided by r divided by t. So you could, in principle, come up with more ways of solving problems. This will come up later, is we're going to use these things and eventually talk about the forces that are acting on objects. So I need to also be clear, this is what's called uniform motion. Uniform motion in a circle. Then you have that these things are true. Now, you can also have non-uniform circular motion. So we're going to work through a problem that deals with that now. I'm going to draw the picture here to start with. Nice big picture. All right, so we have a circle, and we're going to give this thing some velocity. But we don't know what it is. We're going to try to figure out what this is. All right. So what this is going to represent, let's say that there's a car, and it's driving around a circular track. Okay. So if we have this car and it's driving this circular track, well, if it starts at rest and speeds up, it's got to accelerate. It's got to have some acceleration in this direction to get the velocity up. But it's also going in a circle at some point. So it has to have some sort of radial acceleration. Right? So that means that this acceleration is off at some angle somehow. And we can draw that in, say it's something like that. And that, in principle, can be measured because you can just get an accelerometer on your phone or something, or special equipment to measure this. And so let's say that the acceleration is 11 meters per second squared. And let's also say that we can figure out this angle, and it is 30 degrees. Okay. So the acceleration is a vector, and it can have components to it. So we're going to put in coordinates here, right? This is, if you're going through the problem solving steps, one of the things you have to do is put in coordinates. Well, here we need coordinates that are relevant to the fact that this thing's going in a circle. So what I'm going to do is, instead of using x and y like we normally would, we're going to put in a radial component, which I call r hat, and we can put in a tangential component, which you can call t hat. Right. So this thing has some radial component, which we'll call a sub r, r hat. And this is the bit that makes it move in the circle. Right? If you're working through the lab, this should be the fourth lab you're doing. And so you've already done the video lab, I hope, for the projectile motion. But we have one that's for circular motion. And the idea is that if something's speeding up, you should see something that looks like this. And it should mean that there's a radial component to the acceleration plus a tangential component to the acceleration. So we can figure out what those components are. And that shouldn't be too hard. If we fold our paper in half here for a moment. So let's just figure out what they are. They're just vectors, right? So we can put in our radial component. The way we look at this, the tangential component is going to be in that direction, and the radial component is going to be in this direction. So the radial component should look like the acceleration times cosine theta, which is 11 meters per second squared times cosine of 30 degrees. Right? This is where we grab a calculator. 11 times 30 cosine. We get 9.53 meters per second. Now we can do the other thing. This is we can get the tangential component. That's just the acceleration, right? Just the length of it times, in this case, sine theta, because it is opposite to this angle that we've drawn in. And so this will be 11 meters per second squared, sine of 30 degrees. Sine of 30 is a half, so I know this is 5.5. I'll put it in the calculator. There we go. So now the other question is, well, what is the speed at the particular instant we're describing this motion? Well, that depends on the radius. We need to put a radius in at some point. I should have done that in the beginning. This will be R is 4 meters. So we can put in for the radius and the acceleration. All right, we have acceleration is v squared over r. You did this in the math review lab. V is square root of r times this acceleration. Square root of 4 meters times, and then we put in 9.53 meters per second squared. There should be a squared here. I'm running off the page, sorry about that. But we'll see, 4 times 9.53, take a square root, is the radial bit is 6.1, sorry, this is the velocity, 7, and then what we have is meters per second squared times meters, so everything squared, take a square root, should be meters per second. So that worked pretty okay, right? It's basically we used these formulas that we got, and we basically just used the one formula. There is one other thing we can find here. We can say, well, what is the time that it goes around? And so what we can do that is time looks like, well, looking at this equation, we just move the time up and the velocity down. And so the time should be 2 pi r over v. It's not too bad. And then we put in 2 pi times 4 meters. And then we put in our velocity that we found. And we should get some time for this at the moment, what the lap will be. So we're not actually certain of this. All right, this is in principle, we could find the time if it went at that velocity. And so we'd have 2 times pi times 4 meters divided by 6.17. That would be about 4.1 seconds. Now, this is a problem, is this velocity is not constant. So the time should actually go down. It should be less than this. And this is kind of preview, is that to handle these problems, what we're eventually going to do is talk about rotational motion. We're going to have to define things in terms of something rotating around. So that comes up later. That comes up after we do forces and energy and momentum. But you may see that, you're going to get a big packet of notes soon. So you may see that, and just don't worry too much about it. In general, we try to stick with asking you questions that make sense at the moment. So you're going to see this here, like this. We'll do another problem like this. And then we're going to talk about forces, and so we'll talk about the forces that cause things to go in a circle. And if you understand forces that cause things to move linearly, going in a circle is no big deal. It really isn't. It just means that you have, the same stuff going on, but now one of your forces pulls you in towards the circle, or the sum of your forces pull you into the circle. So we'll do this. We'll do another problem like this, and we'll see how it goes.